Hello, I'm Erin Sheridan, and thank you for listening to my talk. I'm a member of the Levy Lab at the University of Pittsburgh, and before I begin, I would like to thank my colleagues in the Levy Lab, our collaborators at UW-Madison, and also the funding agencies that have made this work possible. So today I'm going to talk about the terahertz spectroscopy of graphene and graphene nanoribbons using lanthanum aluminate strontium titanate nanojunctions. So let's begin. Graphene remains at the top of this new class of two-dimensional materials, and that is due to the fact that it keeps presenting us with fascinating optical and electronic properties that promise great strides forward, both in fundamental physics and in device applications. One such property is the fact that the absorption of graphene from the UV to the near infrared is defined by the fine structure constant to be constant at about 2%. This is a surprisingly large absorption for a single layer of atoms, and that leads to a transparent conductor at relevant technological wavelengths. But for other applications, a stronger light-matter interaction is desired. So many methods for increasing the absorption of light by graphene in this range have included putting plasmonic nanostructures on top of the graphene, wrapping graphene around core shell resonators, or critically coupling it to photonic crystals and adding back reflectors. Today I'm going to talk about a method that we've developed to achieve nearly 100% absorption of visible to near infrared light in graphene without having to cover it or use complex metallic structures. I'll begin by talking about the material system in which we realize our devices, and that is the lanthanum aluminate strontium titanate, or LaO-STO heterostructure. The interface between these two complex oxides is rich with interesting physics, but what's most important to note is the thickness-dependent metal-insulator transition that occurs. When there are fewer than 3 unit cells of LaO on top of STO, the interface is insulating. When there are greater than 3 unit cells, the interface becomes conducting, and a two-dimensional electron system forms. If we remain at this critical thickness, we're actually able to reversibly tune the conductivity between insulating and conducting, for example, by applying a backgate to the sample and changing the polarity of the applied voltage. In the Levy lab, we've developed a method to locally modulate this metal insulator transition, and that is through conductive atomic force microscope, or CAFM lithography, and it works something like this. We start with LaO grown on top of STO at the critical thickness, and then we define contacts to the interface. We then bring a conductive AFM tip into contact with the surface of the LaO. When we apply a positive voltage to this tip, we deposit protons on the surface of the LaO. These in turn attract electrons to the interface, locally modulating this metal insulator transition. When we apply a negative voltage to this tip, we effectively remove the protons that we deposited, erasing the nanostructure we created. Using this method, we can create conducting nanostructures as small as 2 nanometers in size, and it is reversible and reconfigurable, which leads to the analogy of an etch-a-sketch, but at the nanometer scale. One kind of device that you can make using CAFM lithography is this simple 4-terminal device that is a nanoscale terahertz generator. So for this device, we draw a conducting nanowire between a source and a drain electrode. We then create a 10 nanometer gap by cutting this nanowire. And then we draw connections to 2 voltage sensing leads. So we apply a DC bias from source to drain, and then we're going to measure the photovoltage generated when ultrafast pulses are incident on this nanojunction here. So this is mysterious. How can a simple 4-terminal device generate terahertz radiation? Well, that is due to the third-order nonlinearity of strontium titanate, which is the strongest known in the solid state. So, as I mentioned, we have a DC bias from source to drain that's highly confined in space at 10 nanometers, and that's multiplied into 2 optical fields. These are highly confined in time to femtoseconds from our ultrafast laser. As a result, we're going to get a third-order nonlinear polarization as a function of the difference frequency that is highly confined both in space and in time. Pictured here is a schematic of our experimental setup. Ultrafast pulses leave our tau sapphire oscillator, enter a pulse shaper, and then enter a home-built compact Michelson interferometer. Within this interferometer, there is a 50-50 beam splitter, And the upper beam hits an optical delay line, which is comprised of a mirror mounted to a piezo stage. The two beams are then recombined at the beam splitter and then focused with a high numerical aperture 100x objective onto the nano junction. We then measure the photovoltage generated as a function of this time delay tau between the two input pulses. Using this method, we have demonstrated that the LaOSTO nanojunction serves as an ultra-broadband, tunable, quasi-monochromatic terahertz source and detector. So we can generate terahertz radiation at over a 100 terahertz range, and more information can be found in this publication here. We're interested in using this platform to study individual nanoscale objects, such as single gold plasmonic nanorods, semiconducting quantum dots, individual graphene nanoribbons, or even graphene itself, which I'll be talking mostly about today. Due to graphene's less than 1 nanometer thickness, we are able to perform CAFM lithography through the layer. So when we apply a voltage to our AFM tip, we can then create conducting nanostructures at the interface directly beneath the graphene. So using this method, as depicted here on the right, I create a 4-terminal nanojunction directly underneath the graphene. What's important to note here is that due to the very small dimension of this nanojunction, when I apply a 1 volt bias between source and drain of my nanojunction, I'm able to generate an incredibly strong electric field localized to within nanometers directly beneath the graphene. So before I show some more data, I want to look at a typical signal. So pictured here is a typical time domain photovoltage signal. So one thing here to mention is that the signal is asymmetric in the y-axis, and that is due to the nonlinearity of our device. We then take the fast Fourier transform of this signal to look at the power spectrum. And there are 3 relevant regions of the power spectrum to look at. There's the linear response, there's the difference frequency generated response, or the terahertz, and then there's the sum frequency generated high energy response as well. So the question we're asking is, how do these different responses change as we tune the chemical potential of the graphene? The main data for this experiment is on the right here. So we're going to tune a global graphene gate and then measure our time domain photovoltage signals. And something fascinating occurs at certain gate values. So for example, at minus 300 millivolts, we see the time domain signal is starting to split up. And in the corresponding power spectrum, we see a nearly 100% extinction of the visible to near infrared light. That's narrowband. Now let's zoom into that. So here's a comparison between 2 different gate values. And we see at minus 300 millivolts, there's a more than 4 order of magnitude extinction at around 390 terahertz. And when these extinction features occur, we see an enhancement of the nonlinear responses of our nanojunction. In addition to tuning this global graphene gate VGR, we can also use local gates to tune the response of our junction. For example, we can tune the nanowire gate, which is an offset applied to the nanowire itself. And we can tune the chemical potential of the graphene that way. You can see here on the right, when we measure the resistance of the graphene versus this nanowire gate, we see our charge neutrality point and also a secondary Dirac feature, which could be a signature of inhomogeneous doping in the graphene. When we look at the time domain signals and power spectra from this experiment, we see something very similar. We see extinction features appear in the visible to near infrared and in the second harmonic signal as well, which is incredibly interesting. And again, as when we integrate the relevant regions of the power spectra, we see that the nonlinear responses have a local maximum around where these extinction features occur in the gate. And additionally, there is a maximum where this charge neutrality point is. So to summarize, we are observing nearly 100% absorption of visible to near infrared light in an energy range where graphene typically does not have a strong light-matter interaction. So there must be some way to explain this. One proposed explanation is that due to the very strong electric field directly underneath the graphene from our nanojunction, the graphene in that region could be acting as a highly doped graphene nanoribbon or nanodisk. Highly doped graphene nanostructures can host plasmons in the visible to near infrared range and subsequently have plasma absorption at high energies. So to study this explanation, we can make a very similar device with a single graphene nanoribbon. So on the left here is a schematic of a graphene nanoribbon in a nano junction. And on the right, you see an AFM image overlaid with a device pattern. And where a nano junction is, you can see there's a single graphene nanoribbon isolated. In a preliminary result, here a power spectrum shows that there is a visible to near infrared narrowband extinction observed in the nanoribbon device as well, which seems to agree with our interpretation so far. So to summarize, the LaOS-TO interface provides a platform for ultra-broadband terahertz spectroscopy. When using this platform to study graphene, we observe spectrally sharp, gate-tunable, near 100% extinction of light in the visible to near infrared. And we propose an explanation that the graphene is acting like a graphene nanostructure, and similar results have been observed in graphene nanoribbon LaOS-TO nanojunctions as well. So that will be the object of future research, in addition to placing 2 nanojunctions on graphene and studying how they interact. And if you're interested in the rest of Levy Lab's work, I recommend looking at these talks up here. And thank you for your time.